Welcome everyone. Lecture 8. Hopefully this will be a somehow simpler class to follow than last class that was sort of heavily theoretical. What we are going to do today is really, after 2 or 3 slides of recap of what we have seen in the past lecture, we'll go into really sort of practical application of density functional theory. We'll first discuss how you set up calculations, that is, what are the parameters and what are the objects that you manipulate when you do an electronic structure calculation. And then we'll start seeing a number of examples to give you the feeling for the properties that we can calculate using density functional theory, for the accuracy and for the pitfalls you need to be careful with. And in the next class on Thursday, we'll finish up with more case studies. So let me actually spend 3 slides to recap what we have seen in the last lecture. Starting somehow from this, that I would say is the most fundamental one, and it's really rewriting quantum mechanics. So this is really the Schrödinger equation from the 60s, density functional theory, and this is what it says, that we don't really need to solve a many-body differential equation to find the ground state charge density and the ground state energy and the ground state properties for a system. But we can actually solve it using a variational principle on the charge density. And the functional that has to be minimized is written here. That is, for any given charge density n prime, we have, at least in principle, a well-defined functional, and we need to change to vary the charge density n prime, and the minimum value that this functional will take is actually the ground state energy. Somehow, sort of the weakness of all of this is that everything is well defined in principle, but it doesn't work in practice. To remind you sort of what were the sort of conceptual step, what Hohenberg and Kohn proved from their first theorem is that given any charge density n prime, more or less any charge density n prime, an external potential V prime is well defined, for which that charge density is going to be the ground state charge density. This was sort of the inverse part of the first Hohenberg and Kohn theorem. And then, at least in principle, the solution to the Schrödinger equation corresponding to V prime is well defined, and we call that psi prime. And so one can construct a functional f that is just the expectation value of psi prime over the many-body kinetic energy operator plus the many-body electron-electron interaction. And so this here is the well-defined, at least in theory, density functional term that is here. And the other term is just the integral of the external potential times the charge density. So everything is well-defined in principle, and so in this, it's a perfect reformulation of the Schrödinger equation. The real problem is that we don't have an exact representation of this universal density functional. And so what Walter Kohn and Lou Sham did was they tried to figure out an approximation to that universal functional. And so in the total energy functional, this was their choice for the approximation. That is, what they said is, well, let's try to figure out what are the most relevant physical terms in this functional, and then we'll sort of sweep under the rug all the many-body complexity of this problem, and we'll call that an exchange correlation functional. That is really where the fine detail of your solutions are. And so what they said, in this universal functional, we can extract terms like the Hartree electrostatic energy written here, that is a very simple and well-defined functional of the charge density. The sort of second term was the tricky one, because they wanted to figure out what was a significant contribution to the overall quantum kinetic energy. And as we have seen, there isn't really a good way to extract kinetic energy. That's basically a second derivative of the wave function, a curvature of the wave function, from a charge density. The sort of most remarkable case is that of a plane wave. A plane wave of any wavelength gives you a constant charge density, but gives you very different second derivative, very different kinetic energy. And so what Kohn and Sham did, they introduced a related system of non-interacting electrons that for a given charge density n, they would have the same, that they would have the same ground state energy of our original problem. But because these are non-interacting electrons, one can define exactly what is the quantum kinetic energy of this set of non-interacting electrons. So if you want, this is just a definition, but it turns out to be a definition of the second piece that makes our third piece here very, very small. So by selecting the green and the red term, we were left with an exchange correlation term that, if you want, still contain all the complexity of this problem that, you know, it's well defined in principle, but we don't know how to solve. But for this, then, they applied the same idea of Thomas and Fermi. That is, they said, well, maybe we could try to approximate this exchange correlation term with a local density approximation. That is, we try to construct this energy term by integrating infinitesimal volume by infinitesimal volume, and each infinitesimal volume will contribute to this many-body problem an exchange correlation energy density that is the exchange correlation energy density of the interacting homogeneous electron gas at that density. So when in 1980 Sepperly and Alder first did very complex calculation, quantum Monte Carlo calculation of the interacting but homogeneous electron gas as a function of the density, this functional, at least sort of in principle, was for the first time parametrized over a whole set of density. Often we call that the Perdue-Zunger parametrization, and so we had finally a working expression. Once we have a working expression, then the problem of finding the ground state becomes our electronic structure computational problem. That is, how to find the minimum of this functional. Note the very significant difference with respect to Hartree-Fock. In Hartree-Fock, we had a variational principle, and that led us to an expression for the energy, or for the Hartree-Fock equation, in which there was a well-defined exchange term, was written sort of somehow complex but well-defined. But because it was basically coming from a variational principle, we had the possibility of making Hartree-Fock better and better by extending our class of search function from Slater determinant to more flexible classes. We could just take, say, combination of Slater determinant. So Hartree-Fock, in principle, can be made better and better in a systematic way, and the computational cost that you will pay is horrendous, but it gives you an avenue. Density functional theory doesn't give you an avenue. It sort of, you know, monolithically states that there is going to be, in principle, a well-defined universal functional, and in the Kohn-Sham sort of decomposition, there is going to be, in particular, one single given exchange correlation functional, but it doesn't give us any sort of systematic route to find better and better functional. And that's why sort of for many years there wasn't really much applied work using density functional theory. Sort of in the early 70s, people started studying very simple system like the surface of a metal just sort of represented as a step in a free electron gas solution. And then it's only sort of at the beginning of the 80s when we had sort of, you know, the parametrization of LDA from the calculation of Sepperly and Alder that people could sort of put together an overall working algorithm. And I've shown you in the last class sort of the phase diagram of silicon. You know, the first time that we see somehow that, you know, this theory is going to give us a very accurate practical result and will be able to give us the lattice parameter, the bulk modulus of silicon, just by plotting the energy as a function of the lattice parameter, or it will give us even the phase transition to high pressure phases of silicon. What I had written in the previous slide was the total energy in this density functional paradigm, and we had as a computational goal now, and you'll see how we address this, the task of minimizing that total energy. And there are sort of two main routes that we can take. Once the exchange correlation potential is written in an explicit form, this is a well-defined, even if nonlinear, functional of these independent single particle orbitals, the Kohn-Sham orbitals, of which the charge density is just the sum of the square moduli. And so we can look at this as a nonlinear minimization problem. We need to find the orbitals that minimize this expression, or as it often happens, we can write the associated Euler-Lagrange equation. We have a variational principle, so we can take the functional differential of that, and that gives us a set of differential equations. That is what we call the Kohn-Sham equation. And again, they are written here sort of not very different, if you look at it, from the Hartree-Fock equations. They are really the same terms. There is a quantum kinetic energy, and now these are single particle orbitals. There is a Hartree term, there is an external potential term, and the only difference is sort of in the way the exchange or exchange correlation term is calculated. In Hartree-Fock, it was an explicit integral of the orbitals. In density functional theory, is going to be some kind of complex function of the charge density. And we are going to try and find out what are the eigenstates of this Hamiltonian, of which the most important part that you need to remember is that this Hamiltonian is what we call self-consistent. That is, it's an operator that actually depends on its own solution. Because you see, what we have is that the charge density is given by the sum of the square moduli, and the charge density goes into the expression of the Hartree operator and goes into the expression of the exchange correlation operator. So the Hamiltonian acting on these single particle orbitals depend on the charge density, and the charge density is a function of the orbital themselves. And so the problem has become slightly different from your usual problem. The Schrödinger equation gives you an operator for which you need to find eigenvectors. Here you have an operator for which you find eigenvectors, but then these eigenvectors give you a charge density that put back in here gives you a different operator. And so exactly like in Hartree-Fock, you have found your ground state solution only once you have become self-consistent. You have an Hamiltonian whose eigenstates give you a charge density that gives you the same Hamiltonian you had calculated the eigenstates for. And so all the computational approaches to solve the density functional problem, as those that solve the Hartree-Fock problem, are iterative approaches. We can't just find a solution to an Hamiltonian, but we really need to make that problem self-consistent. Okay, so this is where we concluded in last class. And so now sort of, we'll actually go into practical feature of density functional theory. Sort of, starting from reminding you that sort of all the quality of your calculation depend ultimately on the quality of your functional. And for many years, the only functional that was used was really the local density approximation functional. In the late 80s and early 90s, people started to develop what are called generalized gradient approximation. That is, they constructed functionals of the charge density that didn't only depend on the charge density itself, but also on its gradient. Not in the sense of a Taylor expansion, because a Taylor expansion wouldn't actually satisfy a number of symmetry properties that we know that the exact exchange correlation functional would do. And so in this sense, all these new approximations are called generalized gradient approximation. And there is a little menagerie of acronyms and symbols that really are sort of built up upon the names of the few people that have really done a lot of work in this field. And so you'll see a lot of John Perdue in this, represented by a P, or Axel Beck in Canada by a B, or Kieron Burke in Rutgers by another B. So these are some of the most popular functionals. I would say that by now, sort of almost everyone has standardized on PBE as being, the most reasonable and the most accurate advanced approximation beyond local density. And so this is what we'll use. There are sort of classes of more complex functionals. The quantum chemistry community has done a lot of work in looking at hybrid functionals, functional in which a certain percentage of the exchange correlation functional comes from the density functional approximation. It could be LDA, or in most cases it could be something like PBE, and some amount of Hartree-Fock exchange is mixed in. So they really take Kohn-Sham equation in which the exchange correlation term has both a component that is density functional theory-like and a component that is Hartree-Fock-like. And some of them, like these two mentioned here, can work very well, especially for molecules. Somehow, again, Hartree-Fock comes from atoms and molecules, and it tends to work better in that limit. Density functional theory is built on an approximation like the LDA that ultimately comes from the homogeneous electron gas, so tends to work better for solids. And as usual, the most difficult cases in which you have a combination of the two. If you want to study a molecule on a solid surface, then none of these two approaches work really exceedingly well. There is a lot of work in sort of developing more complex functionals that tend to work better than any of these that I've mentioned here. They tend to be exceedingly complex. And so again, there are sort of meta-GGA functional. There is a ladder of sort of more complex functional that starts to depend not only on the density and on the gradients, but then maybe on the Laplacian. They might depend on the orbital themselves. So you find terms like exact exchange functional and so on. There is a lot of current work, and there isn't a unique solution. And also they tend to be so much more computationally expensive that at this stage I would say they are still sort of limited to a development effort more than an application effort. But you see, once we have a functional, and this is even done sort of with standard LDA or GGA, we can actually describe with remarkable accuracy a number of properties for very different materials. This is a table that sort of Chris Picard in Cambridge had given me, and sort of you see we have a sort of combination of metals, semiconductors, oxides, alloys, and what we have here, say, is a list of what is the experimental lattice parameter and what is the theoretical prediction. And you see we are sort of in the range in which the errors are around 1%. And I would say for most materials, we are really in sort of in this ballpark. The error on a lattice parameter of a material that doesn't have exotic electronic properties, is not a high TC superconductor, is not a sort of strongly correlated electronic material, can be expected to be in the range of an error that is between 1 and 2%. Okay, so very, very good. You see predictive power. When we calculate with density functional theory the lattice parameter of this, we are really not trying to fit any potential at all. When we calculate the lattice parameter of silver, we are just saying there is going to be an array of Coulombic potentials attracting the electrons with the atomic number of silver, and we are looking at how the total energy of this system varies with lattice parameter. And that's why if you want electronic structure approaches tend to be extremely powerful, because they are not fitted. We are just trying to find the electronic structure solution. Okay, so how does it work in practice? And what I'm going to sort of describe here is what's become known by now as the total energy pseudopotential approach. This is really the approach that has been developed to study solid systems. Sort of, again, you have to keep in mind these two communities, one of sort of solid state extended studies of matter, and one of atoms and molecules. And really density functional theory comes from the sort of solid state approaches. And for reasons that we'll see in a moment that are really related to what we use as a basis set to describe electrons in a solid, what become apparently very early on is that describing accurately the core electron in an atom or in a solid would have been exceedingly complex. If you think at it, whenever you have an atom that forms a molecule or a solid, you have a lot of electrons that are going to be basically unaffected by the chemical environment. If you take an iron atom and you put it in iron as a metal, you put it as iron in a transition metal oxide, or you put as iron as a center, say, in a heme group in hemoglobin or myoglobin, what happens is that the valence electrons of irons will redistribute themselves. But really, the core electron of irons are so tightly bound to the nucleus by order of magnitude in energy with respect to the sort of typical energy of valence electrons that they are basically unaffected. And so, in some ways, we really don't want to carry all the computational expense of describing core electrons when we know that their contribution is going to be a rigid contribution that doesn't change depending on the chemical environment. The core electrons are certainly important. They are there, they are bound to the nucleus, and they screen the nucleus charge. In iron, the 1s electrons, the two 1s electrons, will be so tightly bound to the nucleus that the nucleus doesn't look to the 2s or 2p or 3s, 3p electrons as having 26 protons, but it really looks like having 24 protons because those two 1s electrons screen completely. And so the 2s and the 2p really will also screen almost completely the nucleus from the point of view of the 3s and the 3p. So we want to find out a way of somehow taking into account the presence of that core electrons, but we don't want to carry that on in our calculation because it's very expensive. Not to mention that the spatial variation of core electrons is going to be extremely sharp. I'll show you an example in a moment. And so we need a lot of computational information to describe all the sharp wiggles that core electrons will do around the nucleus. And this problem has been solved, again, sort of from the late 70s to the early 80s by what are called pseudopotential approaches, in particular something that is called, and you'll see this term often, norm-conserving pseudopotentials, that in many ways are some of the most complex part of all these electronic structure approaches, and I'll just give you a sort of generic flavor of how they approach this problem. Okay. Once we have sort of removed the core electrons from our problems, we still need to find out what are the Kohn-Sham orbitals that minimize our density functional problem. And as always, and again we'll see this in the next slides, we need to find an appropriate computational representation of these orbitals. And that is, in particular, will expand those orbitals on a basis. That is, will represent any possible orbital in our problem as a linear combination of simple functions. This is what is called a basis set. So, like in a one-dimensional analysis problem, when you have got an arbitrary function, you can expand, you can do, say, Fourier analysis. You can expand it in a series of sines and cosines. So this same general problem applies here. We have arbitrary functions in 3 dimensions that are orbitals, and we want to find an appropriate basis set that describe them. So this basis set needs to be accurate, that is, needs to be flexible enough to describe all the possible wiggles of our orbitals, but also need to be computationally convenient. And we'll go in that in a moment. So once we have sort of put together these elements, we have sort of our external potential being represented by this sort of nuclei, and somehow via the pseudopotential approach also the core electrons. And once we have decided what is our basis set, we really need to go and solve self-consistently either the Kohn-Sham equation that you have seen before, or we want to minimize the nonlinear energy functional. And so there are sort of several steps. Usually what we'll do is we'll start from a trial solution. Remember that since that the Hamiltonian depends on the charge density, we need to have a guess to our initial charge density to even construct our operator, because our operator depends on the ground state charge density. So since that we don't have the ground state charge density when we start our problem, we need to start with a trial solution. It could be a trial charge density, it could be trial orbitals. But once we have that, all our sort of operator is well defined, so we can sort of calculate all the different terms, the quantum kinetic energy, the Hartree energy, the exchange correlation terms, and we can try to solve that Hamiltonian. From that Hamiltonian, we'll find new orbitals, and with those new orbitals, we'll calculate the ground state charge density, and we'll obtain a new Hamiltonian that then will sort of keep iterating, finding new orbitals, new charge density, new Hamiltonian, until it reaches a fixed point, until it reaches self-consistency. Or we can just take the approach of minimizing the total energy functional to self-consistency. I sort of written in a more sort of compact way the problem here, or well, it'll come in a moment. Okay, so let's describe first sort of our first computational approximation in this problem. That is the introduction of pseudopotentials. And as I said, sort of what we want to do is we want to get rid of the electrons in the inner shells, in the core of the atoms, because they really don't have any contribution to the valence chemical bonds. They are just there, they are important, they screen the nucleus in a very specific quantum mechanical term, but they really don't sort of change much when the valence coordination changes. We call that actually a frozen core approximation. That is, we take an atom, again, we take an iron atom, we solve the density functional problem for the iron atom. That is, we find density functional orbital for the 1s, 2s, 2p, 3s, 3p, and so on orbitals. For an atom, it's reasonable to do that accurate solution even for the core electrons, because you have spherical symmetry and the problem is still sort of fairly simple. And at this point we say, well, from now on we are not going to describe the full iron atom, but we are going always to deal with a pseudo iron atom in which the nucleus and the 1s, 2s, and 2p electrons have been frozen. And so what really the valence electron needs to see is a pseudonucleus that is not given just by the bare Coulombic potential, but by the bare Coulombic potential screened by this 1s and 2s and 2p electron frozen in their atomic configuration. And there is a theorem that we won't dwell into by von Barth and Gellert from the 80s that says that this freezing of the core electrons is actually a very good approximation. It doesn't really matter, it's been verified over and over again, is the last thing we have to worry about. To be precise, the only thing that we have to worry about in density functional theory, apart from making sure that our technical approximations, computational approximation, are all accurate, is the exchange correlation functional. That is truly the only source of error. And so here, if you want, I've represented the idea of a pseudopotential. Okay, this would have been the standard solution for an atom. Actually, here I've chosen something simpler than iron. I've chosen aluminum. And so, we would have had a Kohn-Sham set of equation for aluminum, in which, again, this term here contains the Hartree potential, the exchange correlation potential, and the external potential that would be just the bare nuclear potential. We solve this problem. What we find? Well, we find this hierarchy of states. You see, we find 2 electrons in the 1s state, we find 2 electrons in the 2s, 2 electrons in the 2p, but really the electrons that do all the chemistry are the 3s and 3p electrons. And you see the enormous difference in energy scales. So the binding energy of the 1s electrons to the nucleus is 1500 electron volts. There is no way, unless you are sort of throwing X-rays of very high energy to those electrons, that you are going to affect or perturb in any significant way these 1s electrons. Remember, the energy of a hydrogen bond is 0.29 electrons, is a fraction of an electron volt. So this is 4 orders of magnitude larger. So what we want is, we want to say this set of electrons are so tightly bound that we don't need to consider how they change during the formation of a chemical bond. And so what we want to find is a new potential that we call a pseudopotential, such that the eigenstates in the presence of this pseudopotential give us solutions that really reproduce exactly the valence electron solution of the original atom. So you see, what we want is, we want to go from 13 over R, the Coulombic potential that is contained in here for the bare aluminum nucleus, to a new potential that somehow contains both the bare potential of the nucleus, the screening from the core electrons, and it is constructed according to a well-defined prescription so that the eigenstates of this new set of Kohn-Sham equation are in order, the sort of lowest energy eigenstates are actually the valence eigenstates of our original problem. We get the same eigenvalues, and we get, in a way that I'll specify in a moment, the same eigenfunctions. And so here, it's how we would actually look at this problem. And this is a figure courtesy of Chris Goringer. So you see, what we usually have in an atom is a Coulombic potential, is this thin red line here. This is the potential as a function of the radial distance. So it diverges, it goes to minus infinity coulombically. For aluminum, it would go as 13 over R. What are the solutions, say, for the 1s state in this, what would be the solution for a valence electron in this potential? Well, there are going to be all the sort of core electrons, but then a valence electron would look something like this. It has, you see, this enormous number of oscillations. The reason why those oscillations are there is that eigenfunction of the Kohn-Sham equation need to be orthogonal to each other. This is another one of the sort of, fundamental quantum mechanical rules. It's basically the Pauli principles. You can't have two electrons in the same quantum states, and in particular, electrons corresponding to different quantum states need to be orthogonal to each other. So the integral of, the psi star of, say, the 3s electron in aluminum times the psi of the 1s electron in aluminum needs to be 0. And so what it means is that the higher you go, the more wiggles you have, and these wiggles, that is, these changes of signs, is what allows you orthogonality. Okay, so if you have, a 1s electron that looks like this, a 1s electron will have actually a sort of exponential to the minus r decaying wave function. The wave function, say, already the 2s wave function needs to be orthogonal to this electron, and so it needs to change sign to allow orthogonality when you take the product of these two orbitals. So orthogonality creates a lot of wiggles, and these wiggles also make the sort of charge density coming from a valence electron more spread towards the outside of the nucleus. There is, if you want, another quantum mechanical sort of derived effect in which valence electrons are moved outwards because of this orthogonality constraint. And so you see, this would be, in light blue, the exact wave function for a valence electron. And what we want to find is a pseudopotential that substitutes for the original bare Coulombic potential, and it's written here in sort of with a thick red line, that is constructed so that its ground state wave function, that is here in thick blue, has the same energy eigenvalue of the valence electron, And in many ways, it's identical to the original wave function. And the way we make it identical is actually we only require it to be identical to our original solution outside the core. Because outside the core of the atom is where chemistry takes place. Chemistry will be here when atoms bind with other atoms. Inside here, this is the region where core electron sits, and that's a region that will never overlap with other atoms. Again, because there are sort of already these very strongly bound electrons, and to bring two atoms to have their core regions to overlap requires enormous pressure, sort of hundreds of gigapascals. So we never really have to worry. So what we are trying to do here is we want to construct a pseudopotential in thick red such that its ground state wave functions in thick blue have the same eigenvalues of my original eigenfunctions in thin blue lines, and in many ways they represent the same physics and the same chemistry because they are sort of identical outside the core. So the thick red line is how we describe an atom. The bare Coulombic potential, but with also built in all the screening action from the core electrons. And you see the central feature of the pseudopotential is that if you want, it's become repulsive around the center of the atom, because we really need to keep the valence electron to be mostly delocalized in the valence region. How to build this pseudopotential is actually a complex and somehow dark art. By now, it's been perfected, and there are basically tables of pseudopotential. So it's a problem you almost never have to worry anymore. So an electronic structure code will have a set of pseudopotential. And sort of in the course of the years, there have been two flavors that have been developed. The first one that sort of, was actually sort of, I would say, invented at Bell Labs at the end of the 70s by Hamann, Schluter, and Chang, is what are called norm-conserving pseudopotential, of which I'll describe this plot in a moment. There was a sort of improvement of this norm-conserving pseudopotential that are called ultra-soft pseudopotential, developed by David Vanderbilt at Rutgers University, that tend to be much less expensive to use in practical calculation, basically because they are smoother, and so they can be described with sort of, a smaller basis set, and they tend to be more accurate over a broader range of coordination and energies. But so the general idea of the pseudopotential, sort of, from a different way, sort of in the previous slide I sort of shown you how it looks like, but the generic idea of a pseudopotential is that we want to create something that contains both this nucleus and these core electrons, and that basically will act on the valence electron in the same way as the true problem of core electron explicitly and nucleus. And so what we say is that we want a pseudopotential to scatter an incoming wave, an incoming electron, in the same way as a sort of real set of core electrons and an atom would do that. And in order to do that very accurately for this pseudopotential, what we need to do is actually to have the pseudopotential not just be a single local form, as in the previous slide. I had shown you the sort of red thick line that was just, a unique form of the potential as a function of R, but we actually want our pseudopotential to be different depending on the angular momentum component of the electron coming. So if you have a valence electron and you have a valence wave function, you can actually say that that valence wave function will have 20% angular symmetry of the S-type, 30% of the P-type, 30% of the D-type, and so on and so forth. And what you do is you act differently on the S component of the wave function, on the P component of the wave function, on the D component, and so on and so forth. And so this would be the sort of, the different radial parts of the pseudopotential depending on which components they act. They all have this overall 1 over r or z over r asymptotic trend, but as we get more close to the nucleus, they start differing. You see, from the core region inwards, they are all different, and in particular, they are sort of all, or at least in part, repulsive to, again, sort of represent this frozen set of electrons. And, this is how the corresponding wave functions would look like. And I've made, again, this is for an indium atom, a comparison between, say, the p all-electron wave function and the pseudo wave function. And you see they are identical in the valence region, but in the core region, the true all-electron valence wave function has a lot of oscillation, while the pseudo wave function is much smoother. And this smoothness means that we can describe this pseudo wave function in sines and cosines with a much smaller set of waves at different wavelengths than we would have to do if we had the need to describe all this high frequency oscillation. So at the end, pseudopotential are just there to sort of give us a chance to avoid describing all this high frequency oscillation of the true valence wave function, and also to give us the possibility of avoiding the explicit description of the core electrons that really don't change their shape in going from the atom to the solid. Okay, so now with this, we have an exchange correlation functional. We have this new approximation to the external potential given by a sort of array of pseudopotential centered on each nucleus. And so we are back to this sort of self-consistent problem of having to solve these Kohn-Sham differential equations. And again, the way we want to attack this problem on a computer is by making this problem into a numerical matrix algebra problem. And the way we go about this is by choosing a basis set and expanding our orbitals in a basis. That is, we say by saying that any sort of generic wave function can be thought as a linear combination of a set of simple function for which we can do analytical operation. That is, we are able, say, to calculate the matrix element, say, of the kinetic energy between this simple function, or we are able to calculate analytically the second derivative of this basis function. Well, by making this ansatz, by saying that a generic wave function is a linear combination of this, our problem transforms from a differential analysis problem to a problem of finding these coefficients. And again, sort of the basis set that we'll choose in all sort of our practical computational lab will really be a basis set of sine and cosines, or what we call plane waves, that is especially adapted and especially useful for the case of solids. And I've given you an example here. Suppose that what we want to describe is a Gaussian charge density, okay, sort of something that is a little bit similar to the charge density in an atom. Well, this localized charge density can be actually expressed fairly accurately as a linear combination of very few sines or cosines with different wavelengths. You see, I go from sort of this wavelength to smaller and smaller wavelength, and if I choose my coefficients such that I have constructive interference here in the center and destructive interference outside, I actually get, just by summing 9 terms here, something that basically describes perfectly my charge density. So this will be our general sort of approach to the problem. we choose a basis set, that is, we choose a set of elementary functions that are particularly suited to describe our problem, and for which we can do all the analysis that we want. That is, we are able to calculate second derivatives, we are able to calculate matrix elements analytically, and then our computational problem becomes really just a problem of finding the coefficients. Okay, and this is one of those approximations for which you need to test the accuracy. That is, if you use a very small basis set, if you use only 10 plane waves with different wavelengths, your calculation will be very inexpensive because you have only 10 coefficients to work with, but it probably won't be very accurate. If you use 1 million plane waves, your calculation will be extremely accurate, but it will be also very expensive. So this is an approximation, but an approximation, and this is fundamental, for which you can control the accuracy. That is, you just need to make sure that your basis set is good enough. And that is something that you can always check and test. You can't test, apart from comparison with experiment, if your exchange correlation functional is good enough. That's why we put so much importance, and you should never forget that really all the accuracy or all the errors that ultimately come in your calculation come from the exchange correlation functional. All the other computational numerical approximation using pseudopotentials, using a finite basis sets, are all approximations that can be tested, and we always assume that a well-done electronic structure calculation will have those under control. You are using enough basis sets, you are using accurate pseudopotential, and so on. Okay. As I said, in solids, for reason that you'll see in a moment, really the universal basis of choice is that of plane waves, basically the e to the I complex exponential, and you'll see why. But in a sort of atoms and molecules, sort of the almost universal basis choice is that of combination of Gaussians. And the reason why Gaussians have been chosen, and actually why the sort of most famous quantum chemistry code is called Gaussian, is that it's very easy to do the analytical integrals that are present in the exchange term for Hartree-Fock. So if you want, the exchange term for Hartree-Fock determines the choice of Gaussian as a particularly convenient basis set. And again, the product of two Gaussians is a Gaussians, and that's why this is ultimately a good choice. This is sort of what has developed. At the end, you can still use Gaussians to study solids, or you can use plane waves to study molecule, and there is even a sort of richer phenomenology. And sort of, but generally speaking, these sort of two approaches, that of localized functions in chemistry and of delocalized function in sort of extended systems, are the basic categories. Okay. We'll start from the point of view of solids, and then you'll see why we actually we use plane waves to describe these orbitals. And when you deal with solid, you need to sort of be aware of one of the fundamental symmetries that the eigenstates of a solution in a periodic potential, as what happens in solids, satisfy. That is, in particular, the Hamiltonian of a solid is periodically invariant. Okay, that's the characteristic of a solid. It's a regular periodic array of external pseudopotential that are your nuclei. So in the language of quantum mechanics, we say that the Hamiltonian commutes with the translational operator. Translation operator by a vector that is a direct lattice vector. So if you take a cubic system and you displace, you translate your set of potentials by one cubic lattice vector, you have the same operator. That is trivially to say that if you have a regular array of blue dots that is infinite in space, and you displace them, and the displaced one are crosses, and they have been displaced by this lattice vector R here, and both the red dots and the blue dots are infinite, while by displacing the blue dot into the red dots, you have the same identical problem. Okay, when two operators commute in quantum mechanics, what we know is that we can find eigenstates that are common eigenstates. That is, they are eigenstates both of the first operator and then on the second operator. I won't dwell on this in case you are sort of not familiar with parts of this quantum mechanical problem, but what I want to highlight is that the net result, the fact that we can choose eigenvectors that are common eigenvectors of the Hamiltonian and of the translation operator, tells us that a generic eigenvector for a periodic potential needs to have a very well-defined symmetry and a very well-defined symmetric form. And that's sort of summarized in the Bloch theorem. And that tells us that a eigenvector will be given by a term, a function that has the same periodicity of the crystal times a plane wave, again, a complex exponential that modulates this periodic part and that can have any wavelength. So, in other words, what the Bloch theorem here is telling us is that the solutions, the eigenstates of a periodic Hamiltonian can have any possible periodicity. You don't have to think at the electronic eigenstates of a periodic Hamiltonian as having the same periodicity of your lattice. But the shape that they have is actually this, that is the product of two functions, one that has any arbitrary wavelength, and another term, the so-called periodic part of our orbitals, that does have the same periodicity of the lattice. This can be proven in a variety of ways, and somehow, I summarized here why ultimately this is the shape that the eigenfunction of the Hamiltonian need to have. Basically, because if we have a translation and the Hamiltonian is invariant, the charge density of your solid must also be invariant, and this solution satisfies that, because if you look at the wave function not at R but at R plus a direct lattice vector, this term will be unchanged by definition because this term has the periodicity. This term will become e to the I k times scalar product R plus a direct lattice vector. But when you look at the charge density, that is the square modulus, this term disappears. So only this remains in the charge density. And you also want two translation being equivalent to the sum of the other two. And again, if you translate by two consecutive lattice vectors, this term doesn't change. And the exponential of a sum of two lattice vectors is going to be just the product of two exponential for each lattice vector. But the fundamental concept here is this, that the wave function are modulated by this wavelength, and we actually classify them with these two quantum numbers. As we classify orbitals in the periodic table, we give them quantum numbers. We say this is going to be a 3s electron with spin up. We are saying what the quantum number n, l, m, and spin are for that electron. In a solid, these are our quantum numbers. We have a band index that is, if you want, the solid equivalent of your energy levels, and it's actually a discrete integer index that somehow classifies the different eigenvectors. But those eigenvectors can have also any wavelength, and so the wavelength of the Bloch orbital is another quantum number that characterizes our system. So when you actually look at a molecule, you think in terms of energy levels, and you draw an energy diagram in which you will have a 1s, 2s, 3s energy level. When you think at the possible energy levels for electrons in a solid, you'll draw a more complex band diagram in which you will sort of classify levels not only in terms of discrete integers, but also in terms of the wavelength. And so this is what is usually a band energy diagram, of which I have an example here. So this would be the solid equivalent of the energy levels. So for a molecule, you would have, a discrete set of energy level. For a solid, you don't have only a sort of set of discrete quantum numbers n, but you have also a continuous set of wavelengths. So you have bands that show you how your energy of that eigenvector changes depending on the wavelength of that eigenvector. And what I've plotted here is actually the band energy diagram for a free electron in an FCC lattice. What I'm saying is that suppose that I'm considering an electron that doesn't feel any potential. What would be its band energy? Well, its band energy is actually going to be a parabola. So it's something that we would represent as this. So the energy as being really proportional to its wavelength. That is, again, because a free electron is represented by a plane wave, e to the I kr, and so the second derivative of a plane wave, that is the quantum kinetic energy, is just the k square term, and if an electron is free, there is no potential. So we can think at the energy as a function of wavelength for a free electron to be perfectly parabolic. But now what we can think for a moment is also how to represent this parabola. In principle, this parabola is a single parabola infinite as a function of wavelength. But we can also, for a moment, represent that in an FCC or in any arbitrary periodic lattice. So what we could be saying is that suppose that now there is an imaginary geometric structure that is, say, in real space, a Bravais lattice with FCC periodicity, and that in reciprocal space will correspond to a BCC reciprocal lattice. And what I want to do is I want to take this parabola and fold it. Okay, so instead of having a single parabolic branch that extends to infinity, every time I hit in the Briand zone, in the reciprocal space, a boundary, I fold this parabola back. So what I've shown here is really the band energy diagram that is a parabola, supposing for a moment that my electron lives in the geometry of an FCC lattice. And this is just to give you the feeling that sometimes something that looks very complex is just a representation of something very simple in a specific geometry. And now you'll see in a moment what happens if we study the electron in a system that truly has the FCC Bravais lattice in real space, and so it has a BCC Bravais lattice in reciprocal space, and that is silicon. And you see that, the band energy dispersions for electrons in silicon looked actually very, very similar to free electrons. You see now, for a moment, something that you thought it was always extremely complex, like the band diagram for silicon, turns out to be just a parabola, just a free electron, slightly modified. And you can clearly see all the same pieces, but obviously now these electrons, these valence electrons in silicon, feel the periodic potential, and so the overall solution is modified. And for those of you familiar with solids, there is a band gap between valence electrons and conduction electrons, and here we would be at the gamma point, this would be the lowest valence band, and here we would have the heavy and the light whole bands for the top valence bands. But you know what this is telling us is that electrons in a solid really look like free electrons with a little bit of a perturbation that is enough to transform this parabola into something different. Okay, and again, because they are almost free electrons, and because they have the periodicity, the periodic part of the Bloch orbitals need to have the periodicity of the crystal lattice that we are studying, it will actually be extremely appropriate to use as a basis set to describe at each k point in the Brillouin zone the periodic part of the Bloch orbitals. Will be extremely convenient to use plane waves. And this is the reason ultimately why I written it here, sort of again reminding some basics of crystallography. I've taken, say, the zinc blend structure, so again an FCC lattice here, where these three here in green would be the primitive lattice vectors of the FCC lattice. So what I'm calling here A1, A2, and A3. And these three lattices, three vector lattices in 1/2, 1/2, 0, 0, 1/2, 1/2, and 1/2, 0, 1/2 really represent my Bravais lattice. By repeating blue atoms at any linear combination of these three vectors, I span all the infinite blue sublattice of the cations in a zinc blend, and the zinc blend is just, you know, parent compound of silicon. It's just that the second atom in the unit cell is different, and again, by applying translations that are linear combination of these green vectors, I span all the blue lattice. And silicon would be identical to this, just the red and the blue would be identical. So having defined direct vector lattices, the A1, A2, and A3, what I can define is a set of dual vectors that we call reciprocal lattice vectors, G1, G2, and G3, that are such that the scalar product between G1 and G2 is either 1 or 0, and this is the Kronecker delta times 2 pi. Okay, this is a definition. This is what we know is the definition of the reciprocal lattice vector. But what is very important for us is that these primitive reciprocal lattice vectors are the fundamental descriptor of all the plane waves that I want to use in describing a solid. And the reason for that is that a plane wave written like this, exponential of IGR, where the G here, where this vector is just a linear combination with integer number of my primitive lattice vector, so it's going to be L with L integer, G1 times M, G2 times N, G3, so well defined by the triplet of numbers L, M, N. Well, these plane waves, e to the IGR, for any linear combination of G1, G2, and G3, is a function defined in real space that has a periodicity compatible with the periodicity of my direct lattice. So suppose that we were in one dimension for a moment, and I would have a system that has this periodicity. And remember, the periodic part of the Bloch orbitals will have the same periodicity in real space. So maybe that, you know, the periodic part of that will look something like this, with the same periodicity. Well, then what I want to do is really expand this periodic function as a linear combination with appropriate coefficient of plane waves with different wavelengths, but I need to choose these plane waves to all have the same periodicity of the green lattice. So my plane waves will only look like, this, and this will be the sort of, fundamental harmonic, if you want, and then another plane wave could have this periodicity, and so on and so forth, going to higher and higher wavelength. But sort of, the compact mathematical representation of this is in here. That is, given a direct lattice defined by the three vectors A1, A2, and A3, I can define a reciprocal lattice that is represented by the three vectors G1, G2, and G3, and any linear combination with integer numbers of these G1, G2, and G3 will give me a vector G such that the complex exponential e to the I gr is actually a periodicity that is compatible with my direct lattice. That is, the moment I create a direct lattice, there are an infinite number of wavelengths that are not compatible with the periodicity that I've thrown into my system. Those disappear. I don't want to have anything to deal with. What I'm left is with a numerable infinity of plane waves that are all compatible with the direct lattice that I'm choosing from. And you see, now there is a natural way of both choosing plane waves. They will be here, and also a natural way to choose the most important one, because when we choose our basis set for our calculation, we'll start from the plane waves of longer wavelength. That is the blue wavelength that I've plotted here, and we'll decrease the wavelength. We'll include more and more plane waves that sort of have finer and finer wavelength, finer and finer resolution, and that can be just naturally done by including plane waves with G vectors that have a larger square modulus. Okay, that is, the larger this G vector here, the finer the resolution, the higher the wavelength of this plane wave. So there is truly a natural way to choose basis set now, because again, what we have is a reciprocal space, and so we'll have a Brillouin zone in red. We'll have, if I'm in 2 dimension, the two G1 and G2 vectors, and so the linear combination G's that I've described will be given by the infinite but discrete set of G vectors represented here. And so only the G vectors denoted here with a cross give rise to a plane wave that has the compatible periodicity with my periodic boundary conditions. And so in order to choose a basis set, what I do, I just draw a circle, or in 3 dimensions a sphere, and I decide to include all the G vectors that sit inside that sphere. And by making that sphere larger and larger, I'm going to include G vectors that have larger and larger modulus, that is finer and finer wavelength. And that is what is called your cutoff in your basis set. Okay, so one of sort of the fundamental parameters of your calculation will be choosing your cutoff for your plane wave basis set. That is, choosing the radius of that sphere that includes plane waves with sort of wavelength compatible to the periodic boundary conditions up to a certain resolution. You make this cutoff sphere larger and larger, you systematically include finer and finer resolutions, so you become better and better at describing your problem, and you'll always need to check in your first calculation that your basis set is good enough. That is, by increasing your cutoff radius, you will not see any significant physical change in the quantities that you are calculating. You don't see a physical change in the energy as a function of volume. You don't see a change in the forces acting on atoms, and so on and so forth. Okay, this will take forever. Again, this is not the only choice of basis set, but as you can see, it's really the appropriate one for periodic systems. and it has sort of a set of nice advantages, of which I would say, the most important is the fact that, it's systematic in the sense that you can continuously improve the resolution in your problem by including more plane waves. There is a negative side to this, that since that, it doesn't have any information on how valence electron should look like close to a nucleus or close to a core, it requires a very large number of basis elements. So plane wave calculation tend to have a lot of elements in that. There are a number of sort of other important practical consequences. In particular, as much as Gaussians, they allow for very easy evaluation of some of the analytical terms that we need. So it's very easy to take the gradient of a plane wave or the Laplacian of a plane wave, because basically, the derivative of a complex exponential, if you have e to the I g r, the derivative with respect to r of this is just the function itself times the vector g. This would be the gradient, and the Laplacian, that is the second derivative, is just g squared times the wave function. And so all these terms are easy to calculate. And there is a sort of more subtle conclusion of this, that if you start to have a calculation in which atoms move, like a molecular dynamic calculation, in which you need to calculate things like forces, you need to calculate the derivative of the energy with respect to the position of an atom, but now the energy in itself is an expression that involves linear combination of your basis set. Well, this basis set does not depend on the position of the atom. So there is no term in the force, in the derivative of the energy with respect to the position, that comes from this. If, on the other hand, you were using, say, a Gaussian that was centered on an atom, a Gaussian centered on an atom would have in there the position of the atom. And so in order to take the derivative, the force, you would also need to take a derivative of your basis set. And these are what's called Poulet terms, and that just add another layer of complexity to your calculation. And again, this is, I think, ultimately is one of the reasons why in the solid state community, problems like molecular dynamics and forces relaxation were developed earlier, basically because it's much simpler to calculate forces. And I want to give you here an example on how certain parts of your problem become very easy in your solution. In particular, remember sort of in the construction of the self-consistent operator from the charge density, we needed to construct the Hartree operator from the charge density, the integral of n over r minus r prime. Well, that's basically a solution of what is called the Poisson equation. That is, given a charge density, the Hartree potential is really coming from the solution of this differential equation. That is, the Laplacian, the second derivative of the Hartree potential, is equal to minus, in atomic units, 4 pi, the n electronic charge density, taken as positive here in particular, just to get the signs right. Okay, this is a differential equation. We need to solve it in the course of our self-consistent problem, because remember, we have sort of diagonalized the Hamiltonian, we have gotten some orbitals. From those orbitals, we have calculated the charge density, but now from the charge density, we need to calculate the electrostatic potential, and that's how it works. Well, this differential equation is actually trivial to solve if for a moment you think at a plane wave solution. That is, you think that your potential, that is a function of r, is now being written as a linear combination where the coefficients are called v of g of plane waves. Okay? So I'm taking my potential, it's going to have the same periodicity of the reciprocal lattice, and I'm writing it out as a linear combination of plane waves, and I'm doing the same for the charge density here. So the charge density in itself is going to be given by a linear combination with coefficient g of plane waves. Okay, so this is my expansion in plane waves of these real space functions, and then the algebra is trivial, because to take the derivative of this red term here, what I obtain is nothing else than the sum over g. Second derivative will give me a minus g square, v Hartree of g e to the I g r, and that needs to be equal to, well, minus 4 pi sum over g n of g e to the I g r. So I've done nothing else than inserting the explicit expansion in plane waves of my potential, of my charge density, in the differential equation. And now, well, sort of mathematically, I can actually sort of multiply the left and the right hand term for something like e to the minus I g prime times r, and then I can integrate in the r. And this is just, the mathematical operation that on an orthonormal basis set, as this is, tells me that in order for this sort of equality to be satisfied, what I really need to have is that each coefficient corresponding to the same g vector on the left-hand side and on the right-hand side is separately equal. So the solution to the Poisson-Boltzmann equation is trivial, because what I need to have is that g square vg is equal to 4 pi n g. That is, each coefficient needs to be identical g by g. So if I have a charge density in real space, I can expand it in plane waves, and these coefficients are nothing else than a Fourier transform. So a computer is very good, given a periodic function in real space, to give me these coefficients. And once I have this coefficient n of g, I will know instantly what are the coefficients of the potential that is the solution of this Poisson equation, because those Vg coefficients are really just my charge density coefficient multiplied by 4 pi and divided by g square. So you see, with plane waves, a lot of the analytical work in our electronic structure problem becomes trivial. And here it's contained one of the trickiest part of electronic structure calculation, and the reason why electronic structure calculation of large system becomes more and more computationally ill-defined and more difficult to do as the size of the system becomes larger. Because as the size of the system becomes larger, your cell in real space will become larger, and your Brillouin zone in reciprocal space will become smaller and smaller. As the 3 A1, A2, A3 vectors becomes larger, the 3 dual reciprocal space vectors G1, G2, and G3 become smaller. So the smallest of the G vector will become smaller and smaller as the supercell grows. And so then you see that there is an instability, because this component of the Hartree potential is given by this n coefficient divided by g square. As your system becomes larger, g square becomes smaller, and so a small numerical instability in your charge density gives you a large instability in your potential, and so you need to be more and more careful. You need to become more and more careful in your electrostatic solution as the problem becomes larger and larger. This will take forever to save. I think that I'll need to stop here for today, and what we'll see in the next class on Thursday will sort of wrap up the last few technical details that you need to go into the computational lab on Tuesday, and we'll start discussing case studies for our density functional problem. As a reminder, and I've emailed and hope all of you have received my email, in order to do the computational lab on Tuesday, it is essential that each and every one of you has an independent personal computer account on the computer cluster, because this calculation will become expensive, and we need to run them not on the main central node that will collapse if more than 2 or 3 of you run on it, but we'll need to spool it via queuing system on the sort of nodes of the cluster that lie beneath the master node. Okay, this is all for today. Enjoy the snow, and see you on Thursday morning.